live stream us. See if that works. There we go. I'll double check whether it's actually worked. Here's your thumbs up. All right, I think we're ready. Okay, today we are happy to welcome Chris Byrnes from the University of Sussex to be with us here. We'll be giving a talk on primordial black holes, a potential LIGO-Virgo Kagra, pulsar timing array, and QCD connection. Take it away.
Okay, thanks very much. And yeah, I was saying at lunch, this is my first in-person talk since COVID, so quite exciting. It's been a long time. I've done a lot of online talks where I have no idea if anyone's actually listening, watching, or simply logged in because they felt they had to log in. Okay, you could say I don't know who's in the room because they feel they have to be, but at least I can see of you watching. So that's exciting. Right, so thanks for the invitation. And yeah, the beginning is going to be quite general. Feel free to ask questions as I go. If we run out of time, I'll simply skip some of the more technical stuff towards the end. You know, I won't cry about it. And you can also ask me. I'm here for the whole afternoon, so you can ask me afterwards. Okay, so cold dark matter, I'm not going to repeat the standard pieces of evidence. And some of you guys work on modified gravity. Well, it's very, very hard to explain away the need for dark matter with modified gravity. So the standard answer is it's a new particle, and indeed it may well be, but lots and lots of searches, especially for WIMPs, have not come up with anything. The LHC likewise has not found any sign of SUSY. So the light is supersymmetric particle, I mean, it may still be correct, but we don't have any microscopic evidence for a new particle. So the alternative is that it's in a black hole. Black holes are certainly cold and dark, but an important, the strongest piece of evidence for dark matter is actually structure growth, which came a lot later. And we know that you need to grow galaxies from 10 to the minus 5 perturbations in about 1 billion years. So you need dark matter to do that. You need something really uncoupled from photons, so we cannot have normal stellar black holes. So primordial black holes are a dark matter candidate, whereas astrophysical black holes, meaning dead stars, are not, because it must come first. So that's one motivation, by no means the only one, to study a black hole which formed in the very early universe. That's what I mean by primordial. So let me get straight to one of the key constraint plots, because I haven't worked on it. I'll just show you what they are. So I'll spend a bit of time on this plot. This is FPBH, which I'll mention many times. It's the fraction of dark matter in primordial black holes. So 1 means all the dark matter. Okay, you cannot have more than that, because then you have a problem, but you can have less. And right, the baryonic sector is very rich. We know the standard model has like 20 particles, so why shouldn't dark matter have more than one thing? However, if you're obsessed with having only one thing, then there's basically one mass window between about 10 to the 17 and 10 to the 22-ish grams, where it's still possible to have all dark matter in primordial black holes. On the lower edge...
Sorry, what's that weight in solar masses?
It's down the bottom, very handily.
Sorry.
So 10 to the minus 16 to about 10 to the minus 12. It's sometimes called the asteroid mass window. But these things are basically the size of an atom. That's how small.
Right.
If you shrink an asteroid into a black hole, it's atomic scale, which is pretty mind-blowing. The reason why they can't be even smaller is not because we would gravitationally see effects, it's very hard, but because they were Hawking evaporation. So the temperature is inversely proportional to the mass, meaning that the lighter they are, the more evaporation products there are, and the better your chance to see something. And once you're down to about 10 to the 15 grams, then they're basically fully decayed by today. Okay. Looking towards heavier masses, you've got a constraint from microlensing. If the mass is large enough, you can see, well, you could see in principle the brightening of a background star as the black hole moved between you and that star. The reason why you can't push it down to very, very small masses are twofold. One is the obvious thing that a very small mass doesn't cause much lensing, so the change in the brightness would be very small. But there's a second effect, which is because these black holes are so tiny and because stars are not actually point particles, to the shock of a theoretical cosmologists, they actually have a size. There's an issue that when the black hole becomes too small compared to the size of that star, the apparent size, you're only able to lens part of the surface of the star at one time. That's called the finite source effect. And if you can only lens part of the surface, then the total brightening again will be very small. Then there are all sorts of other constraints on heavier scales around the solar mass. We've got LIGO-Virgo basically calculating the merger rate. And there are all sorts of caveats to all of these. And there's this nice review article by Green and Cabana if you want to know more details. Also, I'm not going to try and be at all comprehensive in my citations. I'm basically just citing where plots came from most of the time. So if you want to, find the literature, well, this review article is one good starting point. Now, personally, even though this, the possibility that all the dark matter are primordial black holes is clearly exciting, it's a window which at the moment there's not very much we can do about. So I'm going to focus much more on the solar mass, if you look down at the bottom scale, where LIGO-Virgo Kagra, right, there are people here working on that sort of thing, are going to get new data. I just had it's restarting in March next year. But we've already got of order 100 gravitational wave merger events. Okay, and as I say, there is some controversy, but it's basically impossible to make all of those constraints magic away.
So how do you know that the black holes that you see aren't primordial?
I'm glad you asked that, because I'm going to.
Okay, sorry.
I'm going to answer that as far as it can be answered, because we have a problem, right? Which is once a black hole has formed, it has no hair. It's got just mass and spin, and the charge is going to be neutral. So there's not that much you can tell. But that's a very good question for me to go on to, because indeed LIGO-Virgo and just started with Kagra, even though it seems unlikely that more than about 1% of the dark matter could be in primordial black holes of that sort of mass range, relevant for these between, say, about 0.1 solar mass and 100 solar mass. That doesn't mean that the actual events we've seen can't be due to primordial black holes. But indeed, because of the no-hair theorem, once it's formed, it's simply a black hole. It doesn't tell you, oh, I formed out of radiation, I formed out of baryons, I'm an X star. They don't come with any labels attached. So we have to look for observables, and they're rather limited. The main one is actually the chirp mass, which is a complicated product of the two masses which merge with each other. So here's an out-of-date plot of neutron stars, the few which have been seen merging. Others have been seen using electromagnetic signals, and black holes. Again, some seen isolated, some seen in the merger product. And one can notice, basically, there's nothing less than a solar mass. That's the Chandrasekhar mass limit, roughly. There's a lower mass gap, but not completely, between about 2 and 5 solar masses. And there's something like an upper mass gap. And LIGO-Virgo would be sensitive beyond the upper range. And not massively beyond it, but nonetheless, there is clear evidence that there's an upper mass gap as well. And these things are kind of predicted, but kind of not predicted. And there's a whole controversy about whether you can explain these mass gaps or not within standard astrophysics.
Where does the other one come from?
Something called pair, pulsational pair. Thank you. Yes, basically they completely explode and leave no remnants above a certain mass.
Oh, cool.
But don't ask me why. Maybe you can say.
That's the hypothesis.
Yeah, it sounds very counterintuitive, right? That the bigger the initial mass, the less likely to leave any relic at all. But where these gaps are, as I say, is really quite hotly contested. And so, right, when you get two objects, you get, in principle, two masses, but you're much more sensitive to the combined mass. And so this is a work I did with Alex Hall, Andrew Gow, a former student, and looking at basically what would be the difference for a astrophysical model, which we took from LIGO. It's quite a simple model, and comparing it to a primordial black hole field. Now, Ignore the fact that there's two PBH lines because they're basically the same. Okay, so we're comparing blue, which is astrophysical model, versus green for a primordial black hole model in terms of the total mass. Okay, that's easy to understand. And you can see that there are, depending on where you put the upper mass gap, basically at some point the astrophysical models say there are nothing beyond it. Likewise, the lower mass gap. But these are free functions where the lower mass gap are. And with the primordial black hole model, you don't have these cutoffs. It can form with any mass scale whatsoever. It's actually a sort of scale invariant problem, as long as you have large enough amplitude perturbations in the early universe on the relevant scale. However, you have a challenge, which is you cannot, in any reasonable way, cut off the mass function too quickly to low mass and high mass. So even though lots and lots of people have worked with monochromatic mass functions, that's clearly ruled out. And well, there's a complicated-ish calculation you can do to calculate a mass function given a primordial power spectrum, but you always have these tails to low and high mass, which is different from astrophysics. Then you can look at the mass ratio. So mass ratio of 1 means you've got two equal masses. Astrophysics tends to prefer close to equal mass ratios because you tend to form the binary first and then go supernova and form the black holes. Although there are different formation channels, primordial black hole models would take naturally a much broader range of mass ratios. So this looks very promising as a way to discriminate, to answer Chris's question. The issue is, unfortunately, the error bars on the mass ratio are large. It's a difficult thing to measure. And finally, redshift in the far future, something like Einstein telescope, would be sensitive to mergers at redshift 30, even 40. And at that point, you should have no stars, right? So no astrophysical black holes. And then the detection in principle of one single merger event at a higher redshift than any stars would prove it's primordial. But that's a long, long way away. I'm impatient to do something before that. So we did this Bayesian model comparison using the events we had back then, which wasn't that many, but already back then, a simple astrophysical model was actually strongly preferred in a Bayesian evidence sense over only primordial black holes. Using these sorts of observational signatures, the redshift didn't give us anything because they're all low redshift. Basically, there's no sensitivity beyond about 0.5 or so. But that's changing. And it's really the total of the Chert mass which dominates the signal. And really the issue is not the mass ratio, but the fact that no matter what we did to our inflationary model, you always get these tails, especially to heavier masses, where LIGO-Virgo should see them if they exist, but they don't find any signatures. There are some caveats. We don't include spin as a computational simplification. And in isolation, that would favor a primordial model because lots of the events seen are consistently to a zero or low spin, whilst intuitively you'd expect if you shrink something like the sun down to a few kilometers, it would be rotating rapidly. But other groups have redone some of our analysis and not reached a different conclusion. So it's just a picture of Alex Hall, who led that analysis. Okay, so even when we really tried very hard to tune our primordial black hole mass function, you didn't get a good fit. However, that's not evidence against a mixed model. It's only evidence against only primordial black holes. And in fact, there's some evidence, again, with caveats by the Geneva group, Franciolini, that adding a secondary subdominant population of primordial black holes actually improves the total phase. The main caveat is that we don't understand the astrophysical formation models well, and they're also being post-dated. Because if you look at what people were predicting before LIGO-Virgo, it was very different. And for example, neutron star mergers were expected to be rather more frequent than they are, and black hole rather less frequent, especially around the 30 solar mass. So what can we?
Actually, that's quite an important point, isn't it? If they're tuning their models to fit this data, and then you're using those models to rule out primordial black holes, it's a bit circular, isn't it?
Yes and no. So as long as one accepts that their models, albeit tuned, can be realized, and they take sort of quite broad prior ranges. So once they've chosen a model, they still choose a broad prior range. If you accept that that you can explain it, then it's still, and it really decisively disfavored. So there's a very strong problem with any primordial black hole model. Even when we've tried adding cutoffs, or even we tried a bimodal mass function to explain sort of the lower mass around 10 and the heavier around 50, then killing it down as quickly as possible, it still wasn't a good fit. But yes, ideally you'd really understand the astrophysical model and subtract it, but we're very, very far away. And like, as I say, like this upper mass cutoff is, you're trying to do a 3D simulation of an explosion of a star with metallicity, and it's just, very, very high. But yeah, I think that the next step really is to do mixed models and to include accretion and to include spin, to do absolutely everything. But this is becoming a supercomputer problem, whereas what we did was run on Alex's laptop. So, but also we'll have many more data points. So even the astrophysical models used by LIGO-Virgo in their first data release are ruled out by their later data releases. And now they're seeing many more features. So you can look in the mass gaps, but you could always have a second generation object formed by a previous merger. So really the best hope, the cleanest signature would be a sub-Chandrasekhar mass. So I know I've talked about this before, it's not such new work, but I'm going to quickly summarize a motivation to look for subsolar mass. Well, one is obviously simply that you cannot form them astrophysically because of electron and neutron degeneracy pressures. Fortunately, LIGO-Virgo is in principle sensitive right down to about 10 to the minus 2 solar masses. So if those things exist, but they have to be very close because the strain amplitude scales with the mass, so it becomes very small. And also the in-spiral becomes very slow for lower masses, so it becomes computationally very expensive to search for a matched template of something which takes minutes or hours versus something which you just see the final 0.1 second or so signal. But this is the QCD now link, which is, if you think in the early universe, you've got the horizon scale. That's the scale of causality, the scale that light can travel in, say, a Hubble time. That's also the distance which gravity can travel. So as the universe grew older, the horizon scale grows larger, the horizon mass grows larger, and this gives you roughly the black hole mass that would form if the initial amplitude of perturbations is sufficiently large. And I'll talk about how large it needs to be in a moment. Now, we're assuming, or I'm assuming, a standard radiation-dominated universe at early times. But within standard model physics, we know there's the QCD transition at a bit less than a GeV energy scale. And by coincidence, this is as the quarks get panned into the hadrons. By coincidence, the equation of state softens the most when the horizon scale is roughly 1 solar mass. And that's just pure coincidence. But it's a very interesting scale. Interesting because LIGO-Virgo is sensitive to it and because it won't be astrophysical black holes if they exist. And so here I'm plotting the equation of state parameters, so pressure divided by density. Why is that important? Well, why are primordial black holes hard to form? Why do most people assume there are none? It's because you've got very high pressure in the early universe. And if you think of a black hole, I mean, squeezing the matter together, well, that's going to be hard when you've got very high pressure resisting gravitational overdensities collapsing. So this reduction in the equation of states, even though it's by only of order 10 or so %, is enough to lead to a dramatic enhancement in the formation rate if the perturbations are enhanced. Basically, you've got lower pressure, so less ability to resist collapse leads to a higher formation probability. And this is based on, well, we don't run lattice simulations, but other people have. So this is pure standard model physics, but we're applying it now to the early universe.
What's the sort of error on that kind of?
On these,
Yeah, the theoretical modeling.
I think they're very small,
Right.
as in the model. The big error we're worried about is how to deal with primordial black hole formation with a time-dependent equation of state. And that's a significant uncertainty because nobody's run a numerical simulation. I think they're talking about like percentage level errors. So yeah, we're not worried about those. And this is back from 2016, but to the best, I don't talk to the QCD community, but to the best of my knowledge, Mark Heinrich does, he was in this paper. People haven't been arguing against the results they found.
When you refer to QCD transition, do you mean when the strong force separates from the other forces, or?
So in the very early universe, right, the quarks are free because you have a sufficiently high energy scale,
Okay.
and then they get bound together.
And that's the QCD transition.
Yeah, yeah, and it's a prolonged process because you've got the 6 quarks with different masses, which is why this takes quite a while. But nonetheless, there's one particular point where it's maximized, which happens to be the solar mass, and that's really one of the nice coincidences in a radiation-dominated background. Okay, so if you take the primordial perturbation amplitude to be very large, much, much larger than on CMB scales, then you get this large peak. This is the mass function of primordial black holes. It's a function of their mass, as I suggested. The dashed line would be if the equation of state was always a third, so pure radiation domination. And what you can see is an enhancement at the solar mass scale by about 3 orders of magnitude. Now, I'm not saying this happened because you need the amplitude of the perturbations to be large enough for anything to happen. But if there is that big boost in the power spectrum, then you preferentially form solar mass over, say, 10 or 100 solar mass by a lot. So that's an interesting observation, and it's a motivation to think that there may be, even though we're not seeing lots of primordial black hole mergers, there might be, if there are some of the 10 or 30 solar mass black holes are primordial, there should be a larger population of one solar mass. And it's not inconsistent with current data because the signal to noise ratio is a lot lower for the solar mass. That is a sort of borderline. It's in the borderline region where, more data should clear things up. Just if that was assuming a scale invariant power spectrum on those scales, again, not on CMB scales. And if you add a scale dependence, the mass function changes quickly. And because you're basically very sensitive to the amplitude of the primordial power spectrum, but the presence of a peak remains true. So that's a reasonably robust prediction. But in detail, to say what would be the shape of the mass function is based on a lot of unknown physics. Basically, primarily, what were the initial conditions of the universe on the small scale corresponding to the horizon scale at the time when it was one solar mass?
So are you saying it's just you're taking the primordial spectrum from the CMB?
No,
No.
I'm saying we can't do that. If you do that, and I will show a plot like that later, you get zero primordial black holes.
Yeah, that's what I thought. Right?
Yeah. That's why this number is much, much bigger than 3 × 10⁻⁹.
Yeah, okay.
Yeah. So no, it would be great if you just took a CMB spectrum, added the QCD transition,
So
and
you're
got.
saying it's got a feature that tilts it up.
You need a big
Yeah,
feature, yeah. I'll show some explicit plots, but yeah, it's absolutely crucial to have some feature. And there are other sort of arguments about non-Gaussianity, about the equation of state, early matter-dominated era. No matter what you do, you still need a feature. You might need a bigger or smaller feature, but you still need one. Yeah. Okay, so yeah, this says that you need a huge boost in the amplitude. Now, you can think then, what happens if my perturbations were not 10⁻⁹, but say 10⁻², what might happen? And then you go basically to the edge of linear perturbation theory. And you've all, I'm sure, taken a sort of basic cosmology module where you're probably told scalar vector tensor perturbations decouple. That's true at linear order, but it's not true at nonlinear order. So when you've got a large amplitude of scalar perturbations, they generate second order tensor perturbations. Okay, that's inevitable. When your perturbations are 10 to the minus 9, who cares about 10 to the minus 18 amplitude perturbations? But when they're 10 to the minus 2, you do care about the induced gravitational waves, the second order. So one can, it's quite complicated, but one can go away and calculate this induced gravitational wave spectrum. Okay. And you can look for it. You need to be careful. You need to work out the relations between the horizon mass and the horizon scale and the frequency of gravitational waves, because they should presumably also be peaked. But I'll show you another nice coincidence in a moment about how we might see this if primordial black holes were generated on a LIGO-Virgo mass scale. And it turns out you're really not very sensitive to FPBH. So as long as there are some primordial black holes, the amplitude of the generated gravitational waves doesn't change very much. Basically, because the amplitude of the power spectrum you need to generate any primordial black holes is already very high. And it's not that much high to get all the dark matter in primordial black holes. So there's quite a narrow window where you would get some, but not too many primordial black holes. And in that window, you then have quite a good prediction for what would be the amplitude of gravitational waves. And if you want to know more, there's a nice review article by Guillaume Dominic about exactly this topic. It's like 100 pages. So all the details in there. Okay, so here's now a plot of the power spectrum. Normally we stare at this part on the left, the CMB. That's where we've measured the spectral index is 0.965, something like that. The amplitude AS is 2 times 10 to the minus 9. Okay, that's right down here. Now on smaller scales, and we're going by, more than about 15 orders of magnitude to smaller scales. That's because primordial black holes over that whole range of mass scales can be detected if there are enough of them, or at the very least, there can't be more than all of the dark matter. So you get a constraint, which are these red and blue lines, which are roughly flat. That's again saying that you're not very sensitive to the exact amplitude of the number of primordial black holes. Why are there two lines? Well, it's because we're thinking about some sort of peak in the power spectrum, again on smaller scales, not allowed on CMB scales, which has to be very large amplitude. If you have a narrow peak or a broad peak, the constraints change. And we had lots of discussions about what's the best thing to plot, how do you parameterize the peak, etc. Now that's primordial black hole line, but I told you that you also are going to get gravitational waves generated at nonlinear and second order. At the moment, the best constraint we've got on a stochastic gravitational wave background, because we're thinking of them forming in the early universe at the same time as primordial black holes, so it would look like just continuous fluctuations, a bit like the CMB from all directions. The best constraint comes from pulsar timing arrays. So these are these very, very stable pulsars, basically for us, very useful clocks, which look for whether there's a gravitational wave passing between them and the Earth, shaking the Earth relative to all those background pulses. And this is sort of summarizing my lengthy title. What's this coincidence? Well, if you think of this as a typical mass scale of a black hole that would form for any corresponding horizon scale K, co-moving wave vector. Okay, so around 1 to 10 solar mass, notice heavier masses are on the right, because smaller K is a larger scale, which is a larger horizon mass. Okay, so LIGO probes around here. This is also around the QCD transition. And it's also, just by chance, the frequency range which pulsar timing arrays are most sensitive to. And so if we compare the constraints again, you should, if you do this sort of analysis, you should be consistent. You should take one particular shape of the peak of the power spectrum and use that to make all your constraints from every possible observable. the pulsar timing array constraint is almost identical in amplitude to that required to generate primordial black holes. So that's saying if there are primordial black holes with a mass which LIGO-Virgo Kagra could see, there should also be a stochastic gravitational wave background in exactly the right frequency band for nanograv or international pulsar timing array to see. And if improvements on these pulsar timing arrays experiments see nothing, then you can really rule out the existence on those mass scales of any primordial black holes. Vice versa, you asked how would you know if something primordial? Well, despite that Bayesian analysis, there's always going to be controversy about, well, wasn't your astrophysical formation model simply too simple? Well, what if I had some more features, like another formation channel? There'll always be a discussion of how do we know something's primordial? Well, I think a better way to approach it is to look for multiple observables, even if they're indirect. And so if nanograv does indeed see a signal of stochastic gravitational wave backgrounds, and it's got the frequency dependence which maps correctly to where you're seeing an axis of black holes with LIGO-Virgo, then that would be a very strong signature towards a primordial origin. And vice versa, you can rule it out. On larger scales, so to the left, there's CMB mu distortions. Don't really have time to go into them, but basically, if you had very large amplitude perturbations, they would act like an energy injection into the CMB plasma. That would make the CMB not a perfect black body spectrum. And so there are also limits on how large the amplitude of perturbations can be on larger scales. And so you see, you cannot form supermassive black holes, at least assuming Gaussian perturbations, as we've done to make this plot. Because the mu distortion band already tells you the perturbation amplitude is not large enough to form any. Because this constraint, mu distortion, is much, much tighter than the PBH band. But on all the much smaller scales, the only constraint we've got at the moment are the non-detection of primordial black holes. And this is Andrew Grau, who led this analysis. So some general messages, again, assuming Gaussian perturbations, assuming that the primordial black holes form from the direct collapse of large overdensities. Once that overdensity has re-entered the horizon, it certainly can't form before that. Then we've ruled out the formation of supermassive black holes. LIGO-Virgo mass black holes, meaning between about 0.1 and say 100 solar mass, will generate stochastic gravitational backgrounds whose frequency is sensitive to the pulsar timing array experiments. And I really mean now, not in the future, but right now. And on even smaller scales, there are simply no competitive constraints. That will change in the future, and I'll finish with a future constraints plot. But for the moment, that's what we've done. Now, I've skipped over loads and loads of details just to give you a little flavor. And I mean, lots of groups have also worked on this sort of thing. You need to be consistent how you make your constraints for one choice of power spectrum amplitude. Some people make the mu distortion, say, assuming monochromatic, but primordial black hole assuming something else. And that's wrong. It doesn't matter when the constraints are very different, because there won't be any confusion about which one is stronger than the other. But when you're looking at the pulsar timing array, the constraints are so comparable that you really need very accurate calculations. You need all your order 1 factors, which in the past, nobody needed to care about. And so, for example, we compared pressure theory versus Peaks theory. And we compared Gaussian window function, top hat window function, etc. And people have claimed there's like exponential sensitivity to these choices. We find that's not the case, as long as you do everything self-consistently. So you have to redo every constraint in the same way, and then you find that, for example, this almost perfect matchup of the two constraints remains. If you do one using one window function, another thing doing a different window function, they no longer line up. And in fact, we found that even the relation between the horizon mass and the black hole mass shifted by quite a lot in a more careful calculation, not just assuming the black hole mass is exactly equal to the horizon mass. And this is not something I've worked on, but Nanograv with 11-year data did find hints of an excess signal, meaning hints of a residual timing discrepancy, which could be explained by gravitational waves. But they don't have enough data to really say it is definitively gravitational wave background. It could be something else. But they've already got about 15 years of worth of data in the can. So, and these things are always subject to delays, but they're expecting a new release this year, which may well, if this hint is true, then with more data, it should become concrete. Now, of course, it may be an astrophysical foreground, which is a signal, and we've never detected a stochastic gravitational wave background, but it's quite likely, I think. And I may be wrong, but speaking to people in that experiment, that they think they will have something. And we're talking on the timescale of a year, not a decade. So it's certainly something to watch out for the next Nanograv release. Okay. Oh, sorry. I need to say that twice. Okay, any questions at that point? If not, I'm re-showing this as an older plot, I'm afraid, just because I didn't have time to remake this. So this discrepancy has gone away with better analysis. But just to sort of show, if you think of the CMB and assume it's NS as a constant, then you've got a slight red tilt, you're never going to form any primordial black holes, quite literally. But how about something more interesting? How about that? Now, I can see why you may laugh. But what would you need to do for that to happen? And in particular, how could an inflationary model generate such a feature? Is it impossible? Is it possible? Are there limits? For example, if the power spectrum can only grow very slowly as a function of scale, then maybe this mu distortion band already rules out the formation of anything to the left of the PTA. And if it can grow very rapidly, then you could look almost monochromatic, and then you can fit in anywhere in the gap. Okay, so we need to ask ourselves, how do you relate a model of inflation to the power spectrum? And I'm going to stick in this talk to single field inflation. So in single field inflation, well, even in multi-field, you've got the epsilon parameter, okay, minus h dot over h squared. That tells you how quickly the Hubble parameter is changing during inflation. And we introduce, there are many definitions sadly in the literature, but our second slow roll parameter, eta, is the rate of change of epsilon in appropriate units. Okay, they're both dimensionless. And then the power spectrum amplitude is h squared over epsilon. And in slow roll, and I stress only in slow roll, epsilon, you can then, so h dot over h squared is also approximately v prime, the derivative of potential divided by v all squared. You can use slow roll when epsilon is approximately constant, and hence when eta is approximately 0. And if that's the case, then you're back to this thing, right? That is the always slow roll prediction. So if you detected primordial black holes, you've ruled out slow roll single field inflation full stop very, very strongly. If we had something like this, what do you need to do? Okay, so, well, okay, we need h squared by the null energy condition should be decreasing. H squared, right, through the Friedmann equation is rho, the density. So that should be decreasing, albeit close to constant. So instead, what we need is the epsilon slow roll parameter to decrease rapidly by orders of magnitude. And that's fine, that can happen, but you're no longer in slow roll. Okay, because if epsilon decreases by orders of magnitude, eta must become large and negative because epsilon is decreasing. So we're interested in models where epsilon is approximately constant on CMB scales, then drops, and then again later becomes constant again, because we don't want this power spectrum to grow bigger and bigger and bigger until the end of inflation, Otherwise, you'll overproduce the small black holes, which is not observationally allowed. Okay. So this is what we need. We need slow roll on the large scales, then some period when eta goes negative, such that epsilon is decreasing, and then something else. Oop. What's going on? Oh, did I not? On my screen, it went all blurry. No. That's weird. Okay, so hopefully you've all seen this in a cosmology class. Okay, the equation of motion for a single scalar field, minimally coupled, gravity, so you've got phi double dot plus 3h phi dot plus dv by d phi equals 0. And what you do, I mean, this is a second order differential equation. What you do in slow roll, well, the potential term, and this is where it gets confusing, the names of things, but dv by d phi is small. So you think, well, the field's going to be rolling slowly at a nearly constant rate. That means the acceleration will be small, so you drop the phi double dot term. So normally when you solve the inflationary equation of motion, you drop phi double dot. But, and that's fine up to a point, but what if dv by d phi becomes 0? What if you have an inflection point? Right? Then you can't drop. You can't say that this is important compared to phi double dot if this becomes very small. Okay. So then, in fact, what's called ultra slow roll is when you do the opposite. Then you drop the dv by d phi compared to the phi double dot term. And then you get something very simple in the limit where h is constant, which is that phi dot decreases like a to the minus 3. So basically, it's saying that you're rolling more quickly than you would want in the slow roll approximation. So you're dumping out kinetic energy until you can recover slow roll. So phi dot decreases very quickly. If phi dot reduces very quickly, you're killing your kinetic energy. And to come back to the slow roll attractor, then epsilon is decreasing very rapidly. And you can show in the limit where dv by d phi is 0, eta is minus 6. Okay. So eta of minus 6, epsilon is decreasing then like a to the minus 6. Your power spectrum is growing extremely rapidly. Okay, thanks. Brilliant. That's what you need to do. So in potential, we'll have to look something like this. It's close to flat, but not perfectly flat. You're in slow roll. Then you have something like an inflection point. It doesn't need to be perfectly flat, but basically the slope needs to decrease by quite a lot. And such that you move to a very negative value of eta. The power spectrum grows a lot, but you can't do this for too long. Otherwise, you could overproduce primordial black holes or even go to eternal inflation. And then you get out of ultra slow roll. Sometime later, inflation ends. So we were interested in how quickly can the power spectrum grow. So we did a matching calculation. This is the curvature perturbation. This is very simplistic for eta basically being 0. So you're in slow roll, then you go to some negative value instantaneously, and then you go back to slow roll. So we did a whole bunch of matchings. This is just one example to see what is the effect of the power spectrum, where you have an appropriate amount of time of negative eta such that the power spectrum grows by about 6-7 orders of magnitude. Okay. And what we found was that for any matching we tried, the power spectrum never grew quicker than k to the 4, and that there was this sort of attractor-ish like behavior where you have an inflection point. You normally do get to k to the 4th steepness of growth, but never steeper. And it's more of an empirical observation than a proof. And the Queen Mary group and others sort of, probed it and found slight caveats, which are interesting, but it wasn't very far away from k to the 4th. Okay. This only happens with transitions, by the way. If you had a constant value of eta, the power spectrum never goes steeper than k to the 3. So that's something is to do with the transitions of eta in and out of ultra slow roll, which gives you this k to the 4th. But as I said, and the first to beat it were the Primordial group in single field, then Tassanat and John Massenot got, with multiple periods of ultra slow roll, managed to also slightly beat it. But we're not talking even k to the 5, we're talking something between k to the 4 and k to the 5. Now, if you add multiple fields, you can actually beat it by a lot, but not in single fields. So, obvious question to ask as well, what difference does this actually make, for example, to the primordial black hole mass function, which is what we use to compare LIGO-Virgo data? And also, are these features which are based on toy models with instant transitions realizable? So, well, it turns out actually, in terms of the primordial black hole mass function, if your power spectrum grows like k, or k squared, or k to the 4, k to the 5, or even for the totally unrealistic case of a delta function, the mass function barely changes at all. You can see for a k growth, it's a bit broader as you would expect because it's growing less quickly, but basically you exponentiate the difference. You're only sensitive near the peak. It matters very little how quickly you grow for the mass function. Okay. Here's just another example of where you've got different power spectra where this is very simplistic again, but you take triangular form, then you add a plateau, and the width of the plateau corresponds to the logarithm of the k max divided by k min. And you can see, roughly speaking, this is on the left-hand side is the power spectrum, and the right-hand side is the mass function. If the width of the plateau is less than about 1, which corresponds to about 1 e-folding of inflation, there's essentially 0 impact on the mass function. So again, you get something close to a log normal, not quite, but quite close to a log normal mass function. And if you want to go away from that, you need something to be really changing quite slowly. Otherwise, it all looks much the same as if you had a more or less a monochromatic power spectrum. So even though you can't have a monochromatic mass function, sorry, power spectrum, the mass function you get out isn't very different. The other question then is, well, you know, ether is not going to jump from 0 to -6 back to 0. There's going to be some smooth transition in the real world. You know, the inflaton potential is not going to go, oh, I'm in slow roll, then instantaneously to an inflection point, instantaneously out again. So we sort of smooth the transition. At the moment, looking at the evolution of ether, in the current follow-up work, we're looking at actually the real inflaton potentials, but that's harder. But yeah, so smoothing the transitions of ether, we looked at what's the effect on the power spectrum, and this was led by Pippa. In fact, it was examined by Bernard Carr, who's on the call. So thanks, Bernard. She's now on Grappa, Amsterdam. And yeah, as you smooth the transition, what you find is that the unsmooth to the solid line, which oscillates. The oscillations are due to the lack of smoothing, which again is a numerical. Well, it's not numerical, it's an artifact of instantaneous transitions. Not going to be present in the real world as you smooth it more realistically up to, say, 1 e-folds versus smoothing. The oscillations go away and the amplitude of the power spectrum decreases. I'm going to skip the next talk, plots. Sorry, just because I want to allow time for questions rather than killing you all with too many plots. But let me show you one more. So here's again the CMB. Here are some potential future constraints, assuming no detection. So mu distortion with a pixie-like experiment, pulsar timing array with a square kilometer array, which some of you guys are working on, I believe. Gravitational waves from LISA or Einstein telescope. And this line here for primordial black holes is assuming there would be really 0 in the entire observable Hubble horizon. And what you can see is, modulo a few gaps, the future is really pretty good in the sense of you should either see the stochastic gravitational wave background at very high significance, or there really aren't any primordial black holes, at least not of a mass large enough to not have evaporated by today. So unlike some of the dark matter candidates, which we'll probably never be able to detect here, because you need quite a violent process to form them with a large amplitude of perturbations, we'll either see them or we won't. Okay, so to summarize, extraordinary claims require extraordinary evidence, and which is why I think, if we wanted to claim a detection of primordial black holes, you need to have evidence in multiple directions. Simply saying we have a better fit than an astrophysical model wouldn't convince many people. So an urgent work, given that we are expecting new nanograv data, is to look for a combined signature in LIGO-Virgo Kagra and pulsar array at the same time. I haven't talked about non-Gaussianity, but there's a degeneracy. But again, with 2 observables, you can break that degeneracy. But to do this, you really need accurate calculations with all the order 1 factors, which until recently simply tended not to be included. And it's hard to relate all of this to inflationary models. People tend to use discontinuous toy parameterizations, which, you've got to start somewhere, but it'd be better if we could work with real potentials and motivate them from something, apart from the fact it gave you what you wanted. So my single sentence summary is, any detection of primordial black holes really would transform our knowledge of the initial conditions and contents of the universe. And even if they don't exist, we still learn something about what the universe was not. And we constrain the power spectrum on more scales than everything else put together. So it's not there.
Thank you very much. All right, I'm going to open the floor for questions. Do you have any questions from people online?
Hopefully that's.
I don't see any hands up yet.
Yeah.
Oh, wait.
Go
Go ahead.